of B6. Okay? And that, finally, after quite a few lines, this is this, which is what we wanted to prove. Alright? So we've proved this part. Now we proved A and B earlier, so we've done all three now, and therefore our mapping function f on remember what we had to prove? So z to the sixth is homomorphic, so tilde equals sign to z, what was it, 3, z2. Okay? So we've done it. So therefore we've proven that these two groups, this one, the direct product group, and Z6, they are isomorphic because they satisfy all these three conditions, well, four in a sense with a bijective, which is sort of two. All three are satisfied. Okay, so next thing. Now that was the next theorem is 36, theorem 36, but it uses parts, well in fact both parts, of theorem 18. Now I don't know if you remember, but in an earlier lecture I got up to theorem 17 and then I said I think I'll skip the last few theorems because I thought they were rather obscure, not particularly useful. Probably Barnard just put them in there for completeness and didn't really help a lot. Well, as it turns out, to prove theorem 36, which will be the next thing that I'll do after going back to theorem 18, because I need theorem 18 to be able to prove theorem 36, this next result after this one. So I will go back to theorem 18, which is on page 45 in your text, if you're following the text. So let's prove that that theorem. It's of two parts. Okay, theorem 18, and it says, well, I'll give you each part. I'll just state it and maybe write it up and prove it each time. So I'll give you part 1 and give its proof, and part 2 and give its proof. Okay, so theorem 18 part 1 is if an element has an infinite order, right? Its order's infinite, then all the powers of x are distinct. So if the order of an element, any element x, is infinite, then every power of that element, x to some integer, and the integer just goes on infinitely, all those powers of x, they're all different, right? That's what we have to prove. All right. So let's start with that. So so we have two powers, any two powers. Okay? So let the element be x. So x just belongs to your group. Yeah, we're talking about groups, right? And let R and S be integers, but so we're saying two powers. If they're the same, if these two are the same, what does that say about R and S? Well, so if these two powers are the same, then that implies that x to the R minus S And you can rewrite that just as x to the r, x to the minus s, right? Just split it up a bit. And now, given that x to the s is equal to x to the r, I can rewrite this all in terms of s's. So I can, instead of x to the r here, I can put x to the s. So that will, this will then be equal to x to the s, x to the minus s. Alright. And you can rewrite this as x to the s, x to the s inverse, right? It's just the exponents, just changing the exponents a little bit. But anything times its inverse is e, alright? So you've proven that. So in other words, x to the r minus s, if this is true, if these two are true, then this is equal to e. Now from, and you're going to have to go back a couple of lectures, but theorem 17 says that if x to the n is e, then n is 0. I don't know if that rings a bell, but alright. So therefore, yeah, if that's your n, if you like, this power here, n, and so that means that r minus s equals 0. So that implies that r equals s. Right? So what have we proven? So if r equals s, these two powers are the same. Okay? These are powers of just some arbitrary element x belonging to your group. So if r equals x, these two powers are the same. Right? Now if r does not equal s, that's sort of, yeah, let me write that out. If s is true, then t is true. But say not t is true. Well, that implies that not s is true, right? Yeah, it's sort of elementary logic. Like if you know, given this example before, but if you live in Xiamen, that's the city I live in China. If you live in Xiamen, you live in China, but you don't live in China. Therefore, you don't live in Xiamen. Well, that's this sort of logic. Okay. So, all right. So if x to the r equals, so if x to the r equals x to the s, then r equals s. All right. Now say r does not equal s, then these two are different. Therefore, x to the r is not equal to x to the s. Okay, and then you've got your proof, right? To part one. Remember, which if an element x has infinite order, then all powers of x are distinct. Okay? So, so if r is not equal to s, so if r is not equal to s, these are different powers, right? You know, x to raised to power r, that's a different power from x raised to power s. You know, so if r and s are different, then x to the r is not equal to x to the s, and that's what you wanted. That's what you're being asked to prove. They're distinct, right? They're different, and that's true for any r or s, because it's infinite. Right? You're not constrained. these powers can go on indefinitely, okay? And they'll be different. So if R and S are different, so you're talking about different powers. If you have different powers, then these x to the R is different from x to the S. Okay? It's sort of this. All right. So that's part one done. Part two is a bit more complicated. It's an IFF, if and only if type, so a two-part problem. All right. Now, if an element X has finite order, right? So little n, it's the order of the element is distinct from order of the group. Remember. So if the order of the element little n is finite, okay, then so put it here. So x to the n is e, right? So there's finite order, so that's the order of the group. Sorry, the order of the element x. Okay, it's so easy to get those two confused, right? Do it all the time. Remember the order of a group and the order of an element, two different things. Okay, so this is the order of the element x. So little n be the order. So x to the n is e by definition. That's how you define the order of an element. Now, okay, so here's the statement of the theorem. Then x to the r equals x to the s if and only if